Lesson 17 is properties of parallelograms, so we're shifting our focus a little bit away from triangles, but we are going to still be using a lot of the things we know about triangles to figure out things about parallelograms. So in 17.1, it's sides and segments in parallelograms. There's two new theorems in this section. So starting in the upper left, it says if a quadrilateral is a parallelogram, then its opposite sides are congruent. So a quadrilateral, that just means a polygon or an object with four sides. And a parallelogram means that it has two pairs of parallel sides. So we can see in the graphic right below this, these have these two little arrows that's saying that they're parallel. So segment AB is parallel to segment DC. And then segment AD is parallel to segment BC. So that'd be a parallelogram. And then this theorem says that because it's a parallelogram, its opposite sides are congruent. So that's important to know. In every single parallelogram, opposite sides are congruent. So AB, the one that's highlighted in green, is congruent to DC, and then AD, the one in blue, is congruent to BC. So that's the first theorem. And then the second one is on the right side. Before we do that, we have to talk about what the diagonal of a parallelogram is. So up at the top right, the diagonal of a parallelogram is a line segment drawn from one vertex to the opposite vertex. So in this graphic right here, those red segments are the diagonals. So they cut diagonally across the parallelogram. So now on to the theorem part. If a quadrilateral is a parallelogram, then its diagonals bisect each other. Remember, bisect means to cut into two congruent halves. So if we look at the graphic down here, you could see one diagonal is segment AC and one diagonal is segment BD. And they each cut each other in half. So BD cuts AC in half. This is two congruent halves. And then AC cuts DB into two congruent halves. So they bisect each other. Okay, and then in this example, we're going to problem solve. So I kind of made the picture really far away from the problem itself for some reason, but just so you know, this graphic goes with this example. So I'll just put it right next to it in your notes. So example 1, consider the parallelogram. Its opposite sides, segment AD and segment BC, have lengths of 14 minus x and 2x plus 2 respectively. What is the length of AD? Okay, so in the graphic, they give us, AD is 14 minus x, BC is 2x plus 2, and we're asked to find the length of AD. So if we go back up to the first theorem that we talked about, if a quadrilateral is a parallelogram, then its opposite sides are congruent. Congruent means the same length. So that means that AD and BC are the same length. So we can take their expressions that go with each side and set them equal to each other to set up an equation. So we do 14 minus x equals 2x plus 2. So 14 minus x, the expression from AD, equals 2x plus 2. And then now I have a one variable equation that I can solve using algebra. So 14 minus x equals 2x plus 2. Usually when you have x's that are on opposite sides of the equal sign, the first priority is to get them on the same side. So we have this 2x right here and this negative x right there. I want to try to get them together. So in order to do that, I have to use inverse operations. I'm going to try to cancel out that negative x. So in order to do that, I will have to add x to both sides. So I would do plus x right here, and then I'll write it under the 2x plus x over here. We're writing it under the 2x because those are like terms, and then just remember that if you use an inverse operation on one side of the equation, you always have to do it on the other side of the equal sign as well to keep the equation balanced. Okay, and then we bring down the 14, and then negative x plus x is 0, so that cancels out. I don't need to write it. Bring down the equal sign. This is 2x plus x, and then remember, if you don't see a coefficient, the coefficient is 1. So it would be 2 plus 1 is 3x. And then bring down the plus 2. And then now I have my x's like all on one side of the equal sign. So my goal now is to get x just completely by itself. So start kind of canceling out the things around it. So if we look at what is being done to it, there's a 3 being multiplied by it and a 2 being added to it. Usually we undo addition or subtraction first most of the time. So I'm going to undo that plus 2 by subtracting 2 from both sides. And then 14 minus 2 is 12. Bring down the equal sign and the 3x. And then I need to get x completely by itself, so I need to figure out a way to cancel out the 3 that's being multiplied by it. The opposite of multiplication is division, so I'd have to divide both sides by 3 to cancel that, like times 3 out. And then the 12 divided by 3 is 4, and then is equal to 3 divided by 3 cancels out, so I'm just left with 1x, but of course we don't have to write the x in front, or the 1 in front of the x or anything like that. So we have our x value, we have like x equals 4, but it's not really what the problem is asking. It's not saying like solve for x. It says what is the length of AD. So in order to find the length of AD, I'm going to take that x equals 4 and put it into the like 14 minus x. That was the expression for segment AD. So 14 minus x. X is 4 though, so a 4 will go right there. So it'll be 14 minus 4, which is 10. So the length of segment AD is 10. And then one other thing before we move on. So technically, like, we set up this problem like knowing that, you know, two opposite sides are congruent. So I didn't necessarily have to use the 14 minus x expression. I could have used the 2x plus 2 one and got the same answer because those two sides are the same exact length. So for whatever reason, like, you just didn't like the way one of the expressions was set up, you felt like it was harder than the other one. If they're opposite sides, they should be the same length, so it shouldn't matter what expression you substitute x into. But either way, we get segment AD equals 10. .2 is about angles and parallelograms, and for this section we're definitely going to build off what we know about triangles. So there's a new theorem here. If a quadrilateral is a parallelogram, then its opposite angles are congruent. So in the previous section we talked about the opposite sides being congruent. This theorem says the opposite angles are congruent as well. So from the graphic on the right, the opposite angles are angle A and angle C. Those would be congruent in parallelogram. And then angle B and angle D would be congruent in a parallelogram as well. So we're going to go ahead and prove that. So in the proof below, given that ABCD is a parallelogram, we want to prove that angle B is congruent to angle D. So angle B right here and angle D right here. And you can kind of tell, like, I already have everything written. I'm just going to uncover it. This is a little bit longer proof, so I think it'd be totally okay if you just like took a screenshot of this after, or this proof is also in workbook 17.2, like all completed. So you could always refer back to that if you need it as well for another example. Okay, so we always start off by stating what is given to us. We were given that ABCD is a parallelogram, so we'll go ahead and state that. And then the reason, of course, is that it's given. And then I forgot to add that in this graphic, they added something, that dotted line. It's called an auxiliary line. It's kind of hard to say, at least for me, maybe not for you, but I'll spell it for you. And the purpose of that line is kind of help us to like create an object within an object. How you can see like that diagonal line cuts the parallelogram into two triangles. And if we can prove that those two triangles are congruent, then we can say that all of their corresponding parts are congruent, which angle B and angle D are like corresponding angles from the two different triangles. Okay, so one of the things that we can start to kind of like use to build up our argument is we can try to find some alternate interior angles from this graphic, because we have, we have two parallel lines, really two pairs of parallel lines, there we go, like the ones that are horizontal and the ones that are more vertical, and then we have that diagonal, which is like a transversal. So remember with alternate interior angles, if we have two parallel lines cut by a transversal, they create these like two sets of alternate interior angles. So like interior means inside the parallel lines and alternate means on opposite sides of the transversal. And those like pairs are congruent to each other. So each like set of alternate interior, like those two would be congruent to each other. And then so would these two. So if we can find that from this picture, then we'll be able to say that some angles are congruent to each other and start to kind of build our argument. Okay, so in order for alternate interior angles to really even be congruent to each other, one thing has to be true is we have to have parallel lines. We know that we have parallel lines because we have a parallelogram. So for 2, we're first just going to state like, okay, what lines are parallel to each other, what segments are parallel to each other. So this says AB is parallel to segment DC. That like those two little vertical bar lines in between segment AB and DC, segment DC means parallel, shorthand. So this is saying that segment AB is parallel to segment DC, and then also segment AD is parallel to segment BC. So segment AD is parallel to segment BC. And the reason that we know that is because we're given that this is a parallelogram, and that's what a parallelogram is. It's a object, it's a quadrilateral that has 2 pairs of parallel sides. So since our like kind of reason is just like, well, that's what it is, we need to write that it's the definition of a parallelogram. Anytime there's like a statement that you put in proof, you're like, because that's what it is, or that's just what it is, like that's what it means. Usually your statement is going to be a definition. So definition of parallelogram, parallelogram is a quadrilateral, has 2 pairs of parallel sides. For 3, we can start building an argument about the alternate interior angles. So for 3, angle DAC, which it'd be DAC, so angle DAC is this one right here, and angle ACB, which is this one right here, are alternate interior angles. And then the second line is just another set of alternate interior angles. So angle BAC, so that's this one right here, and angle ACD, which is this one right here, are alternate interior angles. So they're in between like the pairs of parallel sides. So like if this is a set of parallel lines, and then, sorry, that got a little high. And then this is the transversal. Those angles are inside the parallel lines and they're on opposite sides of the transversal from each other. So by definition, they are alternate interior angles. So for our reason for 3, we would write alternate interior angles, or definition of alternate interior angles. Keep in mind that for like statement 3, these quotes just mean exactly what's written above it. So those 2 pairs of angles are alternate interior angles. And then 3 is just definition of alternate interior angles. Okay, so once we say that angles are alternate interior angles, then we can say that they're congruent to each other, but that always has to be done in 2 parts. So for 3, we've said that they are what they are, and then now we can say that they're congruent. So we say each pair, the first pair, angle DAC, is congruent to angle ACB, and the second pair, angle BAC, is congruent to angle ACD because of the alternate interior angles theorem. So the alternate interior angles theorem says that, if they're alternate interior angles and they're like between parallel lines, then the angles are congruent to each other. Okay, so these 2 things always kind of have to go together if we're trying to use that theorem. First, we have to state that they are unless it was given to us, and then we can use the theorem to say that they're congruent. Okay, and then for 4, we've already kind of like, I'm going to take a step back for a second. So we've said that, this angle and this angle are congruent, and then this angle and this angle are congruent. So of these 2 kind of like triangles that were created by that dotted line, we have 2 pairs of angles that are congruent to each other. If we can get one more part to show congruence, then we can probably use a triangle congruence theorem. So there's no like angle, 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 so that's out, which means we need a side. So think about which side would be easiest to kind of show congruence. It's that side that they share, the dotted line. segment AC. So for 5, we could say that segment AC is congruent to segment AC because anything is congruent to itself. That property is called the reflexive property of congruence. I know it's not the same word, but like think reflection, like if you look in a mirror, you see the same thing back to yourself. So reflection, reflexive, the reflexive property is what tells you that something is congruent to itself. So now we have, those two pairs of corresponding angles that are congruent, and the included side, like the side that is in between those two angles, that's congruent as well. So that's enough to say that the two triangles, like the one on the bottom left, the one on the upper right, are congruent to each other using the angle side angle congruence theorem. So we could say triangle ADC, which is that lower left one, is congruent to triangle CBA, which is that upper right one. The two triangles that kind of make up that parallelogram, and our reason is the angle side angle congruence theorem, because we have two angles in each triangle and an included side. And then once we've said that the two triangles are congruent, we can say any of their corresponding parts are congruent. So now angle B and angle D are corresponding angles in each triangle. So for 7, we can say angle B is congruent to angle D, and then our reason is that corresponding parts of congruent triangles are congruent. That's a mouthful. Okay, so like I said, this is in your workbook. You could also take a screenshot of it, but just to kind of refer back to, I wouldn't necessarily say you have to write the whole thing down. For the next example, we're going to use the theorem that we just proved. So I'm going to go back up to the theorem really quick. It was in the upper left corner, if a quadrilateral is a parallelogram, then its opposite angles are congruent. So if we go back down to our example, it says examine parallelogram ABCD, where the measure of angle A is 5x plus 12 and the measure of angle C is 6x minus 8 degrees. That theorem just says that, if it's a parallelogram, which we have a parallelogram here, it says it in the problem, then its opposite angles are congruent, which congruent means they have the same measurement. So if they have the same measurement, then we can take the expression that goes along with each angle and set them equal to each other to set up an equation that we can solve. So we'll do one angle measurement, 5x plus 12, is equal to the other angle, angle C, which is 6x minus 8. And then now we have a one variable equation that we can solve using algebra. So I always like to, if my x's are on different sides of the equal sign, get them together. So I have a 5x right here, I have a 6x right here. My first priority is going to try to be to get them on the same side. So to get them on the same side, I have to get rid of one from one side essentially, so either cancel it out on the left or cancel it out on the right. I'm going to try to cancel out this 5x by subtracting 5x from it, so that would be 0. And then an equation is like a balance or a scale, so if I do something to the left side of the equal sign like I am here, I also have to do it to the right side over here. I'm going to line up that minus 5x under the 6x because those are like terms. And then 5x minus 5x is 0, so that cancels it out. I'm going to bring down the positive 12, 6x minus 5x. When we add or subtract like terms, we just combine their coefficients. So it would be 6 minus 5, which is 1x, but we don't have to write the 1 in front. And then I would bring down the minus 8. And then my ultimate goal is to get the x by itself. So I need to basically cancel out anything that's being done to it. So there's an 8 that's being subtracted from the x. So to undo subtracting 8, I would add 8. And then if I add 8 to the right side of the equal sign, I have to add 8 to the left side of the equal sign also. So I would do 12 plus 8, which is 20, equals, and then I bring down my x, and then negative 8 plus 8 is 0, so that cancels out. So we get to x equals 20. It's really tempting to stop the problem here because, we solved for x and we're so used to probably hundreds of problems that you did like that in Algebra 1 where you get to stop there. But the question in this problem was, what is the measure of angle A? And angle A isn't 20 degrees. Even if the problem was really bad to scale, be like super unlikely that it'd be 20 degrees. It could be, but anyways, I'm gonna stop. I digress. Okay, so we know that x equals 20. I have to put that in the expression for angle A to find the actual angle measurement for A. So the measure of angle A is 5x plus 12. I'm going to take that 20 that we just got for x and substitute it in there. So it would be, 5x plus 12 degrees. So it'd be 5 times, I'm not going to use parentheses. You can put parentheses around if you want. Just remember it either way to put the degree symbol at the end. So it'll be 5 times 20 plus 12. Remember, order of operations like PEMDAS or GEMS, we would multiply before adding. So 5 times 20 is 100. Bring down the plus 12, and then now I can go ahead and add. 100 plus 12 is 112 degrees. So the measure of angle A is 112 degrees. I'm going to write it over here just so I have a little bit more space. Okay, so super, super important. Like, yes, we have to use an equation and solve for x to answer this problem, but that's not the final answer. It's just how we get to our final answer. So moving down to the very last theorem from lesson 17, right here. If a quadrilateral is a parallelogram, then its consecutive interior angles are supplementary. Supplementary angles means that they add up to 180 degrees. So consecutive means that they're next to each other. So there's a few different pairs of consecutive angles. There's A and D, and B and C, those angles are next to each other. But it can also be A and B, because those are next to each other on the same side, and D and C, because those are next to each other on the same side as well. It's like every combination except for the opposite angles. So it just like wouldn't be A and C, and it wouldn't be B and D. So we're going to list the pairs of supplementary angles. So let's say we go on this side, A and D, or angle A and angle D. And then over here, these two are beside each other. So angle B and angle C. And then A and B are next to each other on that top side. So angle A and angle B. And then one more pair, angle D and angle C. So angle D and angle C. And then just a reminder, consecutive just means, next to each other. They're like two in a row, is what it means by consecutive. Okay, so that's the last theorem. I do just want to add one more example of like a problem solving using this theorem. So we'll just draw a picture really quick. Try to make it look as much like a parallelogram as possible. Okay, that's close enough. We'll pretend these two are parallel even though they don't really look like it. Okay, so, and this is just a little example to add to the end. So let's say we know this is a parallelogram. We know that this angle is 2x degrees, and then we know this angle is x plus 9 degrees. So in this case, we have like two consecutive angles. We don't have opposite angles. So we can't just like set them equal to each other, but we do know that consecutive angles are supplementary. So that means that they add up to 180, so we can set up our equation that way. So we would do 2x plus x plus 9 equals 180 degrees. So 2x and then plus x plus 9. And if you want, like, you could put the degrees around the 2x. You can put, like, parentheses around the x plus 9 and say equal to 100 degrees. If you prefer to just leave it off and add it to the end, that's also totally okay. You'll probably see me doing that more times than, like, writing the full thing out. The important thing is just that you remember to put the degrees back at the end. So we did, one angle, the 2x, and then plus the other angle. Those were two consecutive angles. That means that they add up to 180 degrees. Now we have a one variable equation that we can go ahead and solve. So in this case, the x's are on the same side, so I don't need to use inverse operations to combine them. I just have to go ahead and combine them like regular like terms, where I just add them together. So if there's no coefficient or no number in front of the x, the coefficient is 1. And I add like terms by combining or just adding the coefficients. So it'd be 2 plus 1 together is 3x. And then I bring down the plus 9, the equal sign, and the 180. And then now my goal is to get x completely by itself, so I have to undo the things that are being done to it. There's a 9 that's being added to x, and also a 3 that's being multiplied by it. Usually we undo the addition or subtraction first. So I'm going to undo the 9 that's being added. I'm going to subtract 9 from both sides. I'll bring down the 3x. 9 minus 9 is 0, so that goes away. And then 180 minus 9 is 171. And then from there, goal is to get x by itself. A 3 is being multiplied by x, so the opposite of multiplication is division. So I'll divide both sides by 3. So if I do 171 divided by 3, it's 57. So 3 divided by 3 is 1, so this becomes a 1x, but of course we just write that as x. And then 171 divided by 3 is 57. And now that we got to the end of the problem, I'm realizing like the x doesn't even really include the degrees, so don't write the degrees period here. We'll just like write it in our final answer when we're saying what each angle measurement actually is. So let's say this is angle A and this is angle B, and then we found the x value that like makes their expressions add up to 180. So, to find the actual like angle measurements now, we have to take that x and go ahead and put it into both of the expressions that go along with it. So for the 2x, I can just go ahead and do like 2 times 57. 2 times 57 is 114. So that angle measurement is 114 degrees for angle A. And then for x plus 9, I would put that x equals 57 in for x, just like I did with the 2x. So that would be 57 plus 9, which is 66 degrees. So the measure of angle A would be 114 degrees. And then the measure of angle B would be 66 degrees. Oops, sorry. The measure of angle B, got a little ahead of myself, equals 66 degrees. And then these are really easy to like kind of check really quickly to make sure your answer is like reasonable. We've like set up this whole problem based on the premise that they're supplementary, meaning that they should add up to 180. So to check it really quick, I could just add 114 plus 66 and just make sure that it adds up to 180. It's worth your time to check it. 114 plus 66 is 180, so we're good. Okay, sorry that question was just kind of thrown in there. I just wanted you to get an example with the supplementary angle one as opposed to ones that were like perfectly congruent.